Okay. So before the break, we spoke about this dual fuel concept. I want to tell you more about it. So the modeling was what really set the stage for the subsequent experimental validation. And in fact, I'm convinced that if we had tried to do these experiments before the modeling, we would never have been able to find what I'm going to show you in a minute or two. So the modeling was very, very influential. We have a variety of engines. We actually have, last count, 18 engines at the Engine Research Center. Here are two. This is a heavy-duty and a light-duty engine. I'm just showing you differences in the size of the pistons here. Here's the heavy-duty, the light-duty engine. The heavy is a CAT, the light-duty is GM. They differ in a factor of 5 in displacement. Bore, about 14 centimeters versus 8 here. Let's see what else is different. Similar compression ratios. We can, of course, change these. One thing to note is that heavy-duty engines, as I mentioned earlier, typically have low swirl. Light-duty engines, high swirl. It's arranged by having swirl ports in the intake system of the light-duty engine. We also have a variety of injectors, diesel injectors for both of these engines. And one of the things that we wanted to make sure when we compare light-duty and heavy-duty engines is that essentially the sprays are similar. So one way of looking at that is that if you looked at a picture of the spray plume through a transparent engine, you wouldn't be able to tell whether it's the light-duty or the heavy-duty engine if your scaling, your size scaling was appropriate. So we've done quite a bit of work in that area just to figure out what size hole you would need and what injection pressure and so on in order to get the same spray process and the small and the heavy-duty engine. And so that's all behind what you're seeing here as well. So here are some results for the heavy-duty engine operating at 9 bar RMP, 1300 RPM with an EGR rate of around 40%. And we're using 2 diesel injections, the first 58 before top dead center, which contains 62% of the diesel fuel, and then another one at 30-something, 37 degrees before top dead center. Those were that squish conditioning and ignition pulses that I told you about in the movie. Injection pressure is relatively low for a diesel engine, in this case 800 bar. And what is varying in this plot here, this is pressure, this is crank angle, and down here the heat release curves. What's varying is the percentage of gasoline. So, for example, we changed the gasoline amount from 76% of the total fuel to 89% of the total fuel. And I'm showing you experimental results in the solid black and simulation results that were actually obtained before the experiment, the dotted red here. And what you can see is that as you change the amount of gasoline, in fact, increase the amount of gasoline, you're able to phase the combustion. So you get an extra degree of control here because basically you would want to be able to operate at an optimum combustion phasing. And you can do that by essentially adding less diesel and moving toward more gasoline, gasoline being less reactive. That delays the start of combustion. The other thing is that the width of the distribution here, these heat release rates, is critical, because if you have a very tall spike, you're going to have a high pressure rise rate, and that's going to lead to problems in the engine. And so by optimizing how you introduce the fuel, you can create those gradients in fuel reactivity that we saw in the movie, going from high reactivity regions in the bowl to low reactivity regions in the squish region. It's important to realize that the equivalence ratio is more or less uniform across the whole combustion chamber because we're only injecting about 10 or maybe 20% of the total fuel in the diesel fuel. The rest is pre-mixed gasoline, and that diesel fuel has had time to mix. So the equivalence ratio is roughly uniform. And in that sense, this is homogeneous charge compression ignition. The only thing that's different is that the reactivity of the fuel is stratified. If we were to run just with gasoline, and we tried obviously in the lab, we don't get any combustion because with neat gasoline, it's just not reactive enough to ignite under these operating conditions. And if we run with just the diesel fuel, say very early injection diesel mixed to this equivalence ratio, we would have blown up the engine because these pressurized rates are very, very high, and we would definitely have done some damage. So basically, by having the two fuels, what we can do is extend the combustion regimes from, here we go, extend the combustion regimes that you would have with pure diesel or pure gasoline. You can see that the modeling results were confirmed in these experiments, and also that we can control the time of combustion and the pressure rise rate by changing the details of the fuel introduction. So we call this reactivity-controlled compression ignition, or RCCI, and chose this acronym because it's so similar to HCCI, because this is really HCCI, but it's controlled HCCI by using these two fuels. The other thing that came as a result of this work, and the modeling showed this, and which is what inspired us to do the experiments, was very, very good performance over a wide range of loads. So here we're going from very light load operation to high load operation. What I'm plotting here is, at the bottom plot, the gross indicated efficiency. The blue curve that you see here corresponds to using gasoline and diesel fuel, as I've described. The green curve corresponds to using E85 and diesel. So you have a lot of flexibility in the types of fuels that you use because you can condition the fuel to essentially control the local octane number or cetane number. Interesting thing about that ethanol work, and I'll show you more in a moment, we've achieved the highest efficiencies using that fuel, up to 58% indicated gross indicated efficiency. The baseline production diesel engines of this size have efficiencies around 48 to 50%. So this is a huge improvement in fuel efficiency. And if you take a look at these other plots here, soot and NOx, you see that this is the 2010 EPA required NOx level that all that SCR and after treatment was aimed at trying to reach. We can reach it in cylinder. So basically, when the exhaust valves open, there's no NOx. And the other thing is that the soot levels are, again, compatible with the 2010 emissions levels. So this is very exciting. The other thing that's shown over here is the purple data, where now we thought, well, what if we use gasoline as the low reactivity port-injected fuel, and then we direct inject, instead of diesel, gasoline that has been doped with a cetane improver. I'm going to show you more results on this later as well. But for these particular experiments, we ran with 3.5% of 2-ethylhexyl nitrate. This is this molecule here, which is a widely used cetane improver that you can actually buy in any truck stop. Truckers apparently use it to improve the cetane number of their fuels. And if you consider that the diesel fuel, the total direct injected fuel, is only 10 to 20% of the total fuel, this 3.5% turns out to be about 0.5% of the total fuel would be cetane improver. And this is less additive than you would need for SCR diesel exhaust fluid. In fact, we've done some estimates, and I'll show you that indicate that you might be able to do this every oil change interval, replace a canister of this stuff. So the most important thing, though, is that we can do this type of combustion with a variety of different fuels. So how does it actually work? Well, it's, as I said, controlled HCCI. The heat release occurs basically in 3 stages. And this is shown here from some experiments that we did at Sandia. And of course, we've seen this also in our metal engine experiments. But at Sandia, they used N-heptane to represent the diesel fuel, a more reactive fuel, isooctane to represent the gasoline. And what you see if you look at the heat release rate is you see evidence of the cool flame that's basically due to the N-heptane starting or initiating the combustion. Then you see combustion of a second stage combustion of regions where the N-heptane and the isooctane are mixed. And then finally, the light burn is just the less reactive fuel finally finishing the burn. So basically, by arranging the mixing, you can control the width of this distribution and also the start of combustion by how much of the more reactive fuel you have. And this control is demonstrated vividly here in this plot, where I'm showing you experiments that we did with RCCI, where we just used one injection at 50 degrees before top dead center of the diesel fuel into, or the N-heptane into isooctane air mixture. And we controlled the combustion such that the 50% burn point was constant, 2 degrees after top dead center, over a temperature range from 80 to 170 degrees C for the intake temperature. So you have to remember that with HCCI, you basically, to get a certain combustion phasing, you would have to have there would be just one temperature point, and basically you'd have only one point on this plot. And if it was gasoline fuel, it would have to be a very high temperature. So we are able to get this kind of control by changing the ratio of the amount of gasoline to diesel. And this could be done basically on a next cycle control strategy, for example. So you don't have to wait for the whole air system to purge itself, or for the EGR or turbocharger to ramp up in speed. You can basically do this by deciding on this particular cycle how much gasoline I'm going to port fuel inject and how much diesel I'm going to inject. A huge amount of control from this strategy. So how does it all put together? Basically, we have the red region here would be your high reactivity fuel, the yellow would be your intermediate mixed regions, and the green would be your low reactivity fuel. So we've done quite a bit of work trying to understand the RCCI process, working with Scott Sanders of our group and his students. He has developed a probe that allows you to look at the composition of the fuel and the combustion products through a fiber optic. This just shows a layout of that. So the way this is set up is we can look at two different locations in the combustion chamber. Location A here, which basically is a line of sight down into the page here of the fuel and products in that location in the bowl. And then another location B here, which is out at the squish region. So basically, these are in-cylinder FTIR measurements of the combustion process. And what he is looking at then are spectra. So here we see the cylinder pressure and heat release for an operating point, and the two probes. And what we're showing here is at this green line, just after the cool flame. By looking at the spectrum, this is the wavelength of the emitted radiation that he's picking up from these two probes. You can identify wavelengths where we would expect products to be located and wavelengths where we would expect fuel to be located. And as you can see at location A, which is in the bowl here, we start to see products appearing after that cool flame development. So this is direct experimental validation or verification that we're starting combustion in the bowl, and we're starting to see products being formed in that region. If we move to a slightly later crank angle, so now we're starting on the main stage of combustion here, we see still no evidence of products out at the bowl, at the squish region, but in the bowl now we start to see significant products and the fuel starting to be depleted. These are qualitative measurements, but they're certainly helpful in the sense that they describe what's going on. Then a little later, nearer the peak in the burn here, we see products starting to appear at both locations, fuel being pretty much spent in the bowl region, and then finally all the fuel's gone and we only have products at both locations. So this was very valuable validation of what we saw in our simulation. We've also done experiments at the Sandia National Labs with Mark Musculus again. In this case, the same engine that you saw before. The difference was that he equipped the engine with a GDI engine injector at the side here to, instead of using port injection, to create a premixed mixture of gasoline, or in his case, isooctane, in the combustion chamber. And then the standard diesel injector over here. So the engine is that Cummins N14 with about 14 centimeter bore, 2.3 liter displacement. And in this case, as you see, it's an optical engine here. The camera looked at light luminosity from the combustion process. So this slide here shows the image seen by the experiments. On the left here is the view through the bottom, through the transparent piston. You can see the 4 valves here. And this valve, remember, was replaced by a window. So this dotted line here shows the edge of that window location. And this picture here is the picture seen through the head, through that window. Here's the edge of the bowl, and here's the edge of the liner. So basically, the bowl's to the left of this. Here's the squish region. And what I'm going to show you is a movie with the 2 fuel injections. This is run at a relatively light load point, so it's a little different than the combustion we saw before. You're going to see that the combustion actually starts in the region above the bowl here and progresses inwards. We're operating at an equivalence ratio of about 0.4 here. Here we're using actually quite a lot of the more reactive fuel because we're at light load. I'll show you later that that's one of the advantages of RCCI is you can change the combustion characteristics by changing the ratio of these 2 fuels. Okay, so here's the movie. These 2 little dots that you see here are going to follow the lines here for the pressure trace and the heat release curve. So here's the first injection diesel, second injection of diesel, and then we start to see luminosity. And notice how well controlled it is. It starts from the outside and comes in converging toward the center of the chamber in this particular case. These bright dots here, remember that this is natural luminosity, are basically due to dribble from the injector, which is well known in this experimental setup. So let me show that once again. So if you look at this one down here, you'll see where ignition starts and propagates toward the center. So very well controlled combustion. Okay. So we were kind of interested in comparing the dual fuel combustion with single fuel combustion and those low temperature combustion regimes that we discussed earlier today. So here we're using 3 different engines. The Cummins engine I just showed you with low temperature combustion we discussed before the break. The dual fuel RCCI, which we've done experiments on our Caterpillar engine at the Engine Research Center. And then data from Lund University using ethanol, partially premixed compression ignition. So if you look at the engines, they're all fairly similar. They have roughly the same bore here. Compression ratios are actually a little different because remember the optical engine had a lower compression ratio, but that was accommodated by running with a slightly higher intake temperature and boost to match roughly the compression ratios of the baseline engines. This engine had a higher swirl, but other than that, the engines are fairly similar. So we're operating basically on diesel, ethanol, and then dual fuel. So if we look at diesel LTC, so here we're injecting 20 degrees before top dead center, fairly high injection pressure, and we have quite a high EGR rate to keep the temperatures low. This is what we saw earlier. This is, in this case, a single injection like we discussed before. This is the ethanol, partially premixed compression ignition. Here, very early injection, 60 degrees before top dead center. Give a lot of time for mixing. Very high injection pressure. And interestingly, no EGR because ethanol being so unreactive, you don't really need to rely on dilution to delay combustion. So there's no EGR over here. And then the dual fuel like we've been discussing. Here's the first injection, second injection. So 2 injections at the timings I showed you before. We actually ran this, as I showed you, with gasoline or with E85. Okay, so let's look at the dual fuel RCCI. Here you're seeing pressure trace for two different cases. One is when we run with E85 and diesel fuel, and the other when we run with gasoline and diesel fuel. The E85, you can see from this trace here, has kind of a more gradual rise in pressure, and that's shown also in the apparent heat release curves down here, a more gradual rise with the E85 diesel. The red dotted stuff is the model prediction and solid lines of the experiments. And you see we do a very good job of matching both for E85 and for diesel gasoline combinations. So one of the questions you might ask is, how come we see a different peak heat release rate when we run with the E85 compared with the gasoline? And this plot here kind of helps explain that. This is the mass fraction of fuel at a particular research octane number. So in other words, a PRF number, if you like. When we run with gasoline and diesel fuel, we go from the octane number of diesel fuel at parts of the combustion chamber to the octane number of gasoline in other parts of the combustion chamber. And you can see that, you know, as much as 30% of the fuel still has the octane number of gasoline over here. And in between, we've mixed the gasoline and the diesel. When we run with E85, which has a much higher octane number, above 100, you see that we're essentially extending the range over which this reactivity is stratified over a wider range. And this has the effect, basically, of widening the heat release event and making it more gradual, which is what explains this lower pressure rise rate. Okay, so here we compare then the diesel low temperature combustion, the ethanol partially premixed compression ignition, and the reactivity controlled compression ignition. We're looking basically at a couple of the key intermediates. Formaldehyde predicted in the model, which is an indicator of first stage combustion, low temperature combustion, and then second stage indicated by the OH. If we look at diesel low temperature combustion, we've looked at this earlier. Here's the diesel fuel it's injected, so we see now a large amount of diesel. We see after a certain delay the formation of the first low temperature combustion products. Remember, we're running with a very high ETR here. And then at a certain moment, the second stage combustion where we see OH appearing. If we run with ethanol, we see quite a different looking combustion. Ethanol was injected very early, so here's our high ethanol concentration. And then at a certain moment, intermediates are produced. Here's your formaldehyde, and then eventually second stage combustion. And then finally, for the dual fuel RCCI, so here's the diesel, which is injected in those two pulses, but here we're looking at 3 milliseconds before taptic center here. So here's the diesel fuel. You notice it gets consumed first before we see a change in the isooctane or the gasoline and the ethanol in the E85 case. So you see the formation of the formaldehyde and then the OH. So quite different looking reaction progress with these three different combustion scenarios. If you look at the corresponding heat release rates, you see that with the diesel PCCI, we have this big spike here because basically we pre-mixed the diesel fuel with the air, and at a certain moment it all goes off with a bang, kind of like in HCCI. Ethanol, being so unreactive, takes a long time to cook before it goes off, so now the combustion occurs quite late. And so the low reactivity and also is associated charge cooling because ethanol has a high latent heat of vaporization, so it cools the local temperatures, again delaying combustion. But with the dual fuel, we see basically combustion starting at roughly the same time as it did for the diesel, but we get a long duration combustion because of the spatial gradient in reactivity. So essentially, by being able to control the details of the heat release, we can go to much higher loads with RCCI and essentially extend HCCI operation to essentially the whole engine operating there. Okay, so again, getting back to the fundamental criticism of having to use two fuels, I just mentioned that RCCI is pretty fuel flexible. We could use all kinds of different fuels. In fact, we've run it with fuels that no other engine will be able to run on. We have done some experiments. We'll be reporting on this at the TESOL conference in Europe with wet ethanol. This is 70% ethanol, 30% water. You know, just getting rid of the last 5 or 10% of water in ethanol is where all the expense is in processing ethanol. So if you can run with ethanol with high water concentration, it becomes a cheap fuel. And we can run with that because basically we rely on the diesel fuel to tailor the octane number of the ethanol, and in that way we can create whatever fuel we want, essentially, by mixing the low reactivity fuel and high reactivity fuel. So one of the thoughts we had was, okay, what if you just ran on one fuel, let's say gasoline, and you used the cetane improver in the direct injected fuel? So we've done quite a bit of work. I mentioned the EHN, the ethyl hexyl nitrate. We've also looked at peroxides, dietert-butyl peroxide, which is added to the diesel fuel, the gasoline rather, and injected through the diesel injector. These plots here compare if we just use diesel fuel, the black line, and then the other plots here show various concentrations of DTBP. Basically, even down to 1% levels of this additive make the fuel behave similarly to diesel. And in fact, this is a plot from the publication by the EPA that shows how reactivity can be changed with EHN or DTBP as you increase the additive concentration. You can get an increase in cetane number of on the order of 30 with just 2.5–3% of this additive. So one of the problems with ethyl hexyl nitrate, though, is it has an N in it. And we're concerned, obviously, if you N in the fuel, you're going to get N in the exhaust. And if it comes out as NO and not N2, you're in trouble. So we've looked into that. Here's, we're comparing E10, that's 10% ethanol in gasoline, mixed with EHN, and we're going to compare that with diesel fuel. We're going to have a 3% mixture of EHN and gasoline and compare with diesel. So this result that you see here is E10, EHN heat release rate, running the engine at 5 bar IMEP 1900 RPM. If we run with diesel fuel, with everything the same, we get a slightly earlier combustion, which means that diesel fuel is slightly more reactive than E10 with EHN. And also we can see a premixed burn and the beginnings of a diffusion burn. It's a little bit more obvious than with the E10 EHN. So by retarding the injection a little bit, going from 11 degrees to 9 degrees before tapered center, we can get the combustion phasing to look the same. And then if we increase the diesel injection pressure from 500 bar to 900 bar, so with gasoline being more volatile, we need lower injection pressure than with diesel, we can make the two curves pretty much overlap. So basically, we can make diesel fuel and gasoline, or in this case, E10, look pretty much the same. And in fact, if we do some engine experiments with the two fuels and slight changes in operating condition, we get very similar NOx and very similar particulates. This plot just goes to show the problems with diesel combustion. This is where those EPA requirements are for NOx and SOOP. So we've got to be down here if we want to meet EPA mandates. So let's see what we can do with RCCI. So now we're going to run compare diesel gasoline versus E10 EHN RCCI. In this case, as I said, we have port fuel injection of E10 and direct injected E10 plus 3% EHN. That's in these two columns. We're running at 5.5 bar, 1900 RPM. Notice that we need slightly different amount of these two reactive fuels, again, associated with the fact that we're trying to simulate diesel with gasoline with a cetane improver. We ran with slightly higher injection pressure with the diesel, as I explained. And you can see from the standpoint of a comparison, we're able to get pretty much identical results in terms of pressure trace and heat release. And if you look at the performance here, is at two operating points, 5 bar and 9 bar. Certainly, we get more NOx with the EHN additive, as we would expect, because we're adding some nitrogen in the fuel. But in spite of that, because the RCCI NOx levels are so low, we're still able to meet EPA emissions regulations, which are around 0.23 for NOx levels in gram per kilowatt hour. And at high load, it's no problem. We get actually even lower soot, and these numbers are minute. They're pretty much at the bottom of the range of the measuring instruments. And then as far as the gross indicated efficiency is concerned, very similar results with these two fuels. So it seems like you could get by with one fuel and a very small amount of additive. And we've done a little bit of an assessment of this in this paper here, where we took a representation, 5 steady state points on the a representation of the FTP cycle, and found that basically, if you look at the whole cycle, going from idle, light load operation to high load, high speed operation, that over that whole range, we want 55% of the fuel to be port fuel injected. In other words, 45% to be additized. A lot of that comes from this low load point here, where we need quite a bit of the reactive fuel, because if you have a non-reactive fuel, you can't get the engine to run at light load. And so if you work it all out, it turns out that if we have 3% of the additive, the total amount of additive needed turns out to be similar to that you would need in a diesel exhaust fluid SCR system. And in fact, if we make some assumptions here, you can see that basically for a 10,000-mile oil change interval, the tank would have to be around 2 to 3 gallons of size. So we think that that's pretty reasonable. At least it's interesting. We've also been talking with people who make these cetane improvers, and there's a lot of interest in seeing whether there are other molecules that could be designed that might be useful in this application. So for this part of our presentation here, let me just summarize and conclude. CFD modeling can be integrated with optimization techniques that can help you improve engine design. And in fact, new combustion strategies can be discovered using CFD optimization, like the RCCI that I showed you here, that came basically from modeling results. In fact, after finding it using the modeling, we then went to engine experiments and validated it. What we show is that basically dual fuel or single fuel with an additive can be used with reactivity controlled compression ignition. It gives you the necessary combustion control when you have optimized blending of the port and directly injected fuels. And that this RCCI, in addition, offers you higher thermal efficiency than baseline diesel engines. I'm going to talk more about that in the next segment. And can meet emissions regulations without the need for after-treatment. So it's pretty exciting. Let me take questions now, and then we move to the final part of my presentations. Yeah?
So for the cetane booster, why that molecule as opposed to something like inheptane?
OK, so you need something very reactive. And so these cetane improvers, as you saw, can boost the cetane number by 30 points with just a small amount. Inheptane, obviously, has a fixed cetane number. You would need a lot of cetane a lot of inheptane to increase the cetane number equivalently. But you know, that's what RCCI does, right? If we run with 10% diesel, 90% gasoline, that's sufficient. The idea here was to try to run with 100% gasoline with a tiny amount of cetane improver in the injected fuel. Yeah.
You had compression ratios up to about 16. I'm wondering if it went up to 18 or 20, you may face the problem that there would be knock of the,
absolutely.
Of the injected fuel,
right.
And maybe to overcome that, then you would delay the injection, and in which case you may lead to more suffocation in the mixture.
And
so
more knocks.
Are you worried about?
Yeah. So definitely, in terms of the optimization space, there's a huge number of variables to look for. Compression ratio is one of them. We've been working with Caterpillar. They're very interested in this, and they actually went in the other direction. With a 12-to-1 compression ratio engine, they were able to run at loads higher than 25 bar IMEP. It's because you want to keep the temperatures low enough that you get no knocks. If you go to high compression ratio, you kind of start out with a disadvantage because now you're going to get knocks. And the other thing to look at, if you look at the engine system as a whole, when you go to high compression ratio, you know, your thermodynamics textbook tells you you're going to get good efficiencies. But what it ignores is you also get high heat transfer losses. So, and the other thing is that the friction work increases because of the loading on the piston. So that FMEP we were talking about in one of the first lectures goes up. So, you know, if you look at the whole engine system as a whole, it's not clear that high compression ratio is going to be advantageous. And we're really looking here at more conventional compression ratios or lower. Remember that this is starting to look like a gasoline engine here. Gasoline engines operate at 12-to-1 compression ratio. A high compression ratio would be 12. So, you know, as we start moving towards regimes that are somewhere between diesel and gasoline spark ignition engines, we have to rethink some of these things.
There was some time ago, Scania used ethanol and ignition both diesel combustion. Are you aware what the level of success they got with that?
Actually, I referred to that work here. That was the ethanol PPCI. And it's kind of non-optimal combustion. So it's kind of late because it's very hard to burn that ethanol. We can burn ethanol because we change it from ethanol to something mixed with diesel that's much more reactive. Yeah. Okay, so let me get to the last part. And we can, if there's time at the end of this, spend some time, more time discussing generalities. So we're now going to talk about automotive applications. And obviously I'm going to be talking quite a bit about RCCI here. And then if there's time, I'll talk about the future. So one of the things that Sage Kopchan did in his PhD thesis, which is really a magnificent thesis, was to compare for a light-duty engine, compare conventional diesel combustion and RCCI. And to make that comparison is very difficult to do, but what he decided to do was to say, let me just pick a conventional diesel combustion strategy, the Euro 4 strategy, and keep everything the same as in the Euro 4, the compression ratio, the boost, the intake manifold temperature, the swirl, and just simply switch from the Euro 4 diesel to reactivity controlled compression ignition with gasoline and diesel. And this was a modeling study, as indicated. The engine was the GM 1.9 liter that we also have in our lab, so we had a lot of data available. It has a Bosch common rail fuel injection system, and the data is shown here. We've seen some of this before. So here are those 5 operating points taken from the representation of the FTP cycle, ranging from the light load to the high load points and over a wide speed range. The light-duty engine has to meet emissions targets that are mandated by EPA, like the heavy-duty engines. And the Tier 2 bin 5 is currently the mandated emission level. If we take a look at this table here, you see basically the targets that have been recommended by a group from, I guess they're from Ricardo Consulting Engineers, for each of these modes. These would be the targeted NOx levels to meet Tier 2 bin 5 in grams per kilogram fuel. Now, the Euro 4 baseline, which does not meet Tier 2 bin 5, NOx levels are shown here. Much higher NOx, for example, at this high load operating point. So what we're going to do is we're going to take those Euro 4 data and we're going to allow the use of diesel exhaust fluid in the amount of 1% per gram per kilowatt hour of NOx reduction required. And this is a recommendation that Tim Johnson, who's very active in this field, has made. And the other thing is we're going to allow for optimizing the Tier 4, the Euro 4 operation to kind of reduce the amount of exhaust fluid needed as much as possible. So that's going to be our comparison. So this just shows the 5 operating points in terms of numbers. You can refer to these later, but basically here's the engine speed range, the indicated mean effective pressure range associated with those 5 points. Let's see, you notice that for Euro 4, you run with pretty high EGR, except when you get to the high load point. These are the common rail injection pressures. Very early injections, basically, I'm sorry, very late injections. The main injection is mostly around top dead center. And the reason for this is that basically you want the combustion to occur in that late injection mode that we discussed, where you can minimize NOx as much as possible by essentially having the combustion take place during the piston expansion when temperatures are decreasing. In each case, there's a pilot injection and then the main injection shown in these red pulses here. So this is basically the Euro 4 baseline data, and here's the experimental data that we have available. What you see here is the experiment in blue, the simulation results in green. Not perfect agreement, but we thought these were good enough for this type of study. In fact, here's a comparison of the predicted NOx for the 5 different modes, predicted soot, and predicted gross indicated efficiency. And if we use the recommended weighting from the group that recommended these 5 operating points and weight the results, what we find is kind of a cycle average emission, showing here cycle average NOx from the experiment in blue and from our calculations in green, and cycle average soot. And then here, cycle average gross indicated efficiency. And what you can see is that the model and the experiments agree pretty well. So we're confident in our model over this wide range of operating points. And also shown here is Tier 2 bin 5. This is what the Euro 4 has much higher NOx values than the Tier 2 bin 5 requirement. So to meet this, what the engine manufacturers have done is recalibrate the engine and then apply SCR exhaust after treatment. And that's what we want to compare against. So just as an example of a recalibration here, if we just take one of these modes, mode 3 here, this late injection case here corresponds to the Euro 4 calibration. If we inject earlier, we get this blue curve here, so earlier combustion, much higher pressurized rates and therefore noise, and also higher in-cylinder pressures, much higher NOx, as we'll see, but now we'll use the SCR to bring this back down again, to bring the NOx back down. So that's just one example where you see the difference between the Euro 4 and the Tier 2 bin 5 calibration. Again, a really busy table here. I don't really want to spend any time on this other than to show this column. I'm going to be comparing CDC and RCCI in a minute. And what we found is when we looked at the whole cycle, it was actually very advantageous to have pure diesel fuel for mode 1, which is kind of an idle point, with high EGR, even higher than the Euro 4 EGR, in order to keep NOx low. So basically here we have, where am I? Okay, 2 injections. The injection pressure is 500 bar. Injection at 16 before the main injection, and here's the main injection. If we go to the other, if we move along this line here, we see that for mode 2, mode 3, mode 4, we don't need any EGR with RCCI. Whereas with the conventional diesel, you still have to maintain high EGR and therefore high pumping losses. And then finally, we introduce EGR at the high load point in order to reduce NOx with RCCI. So those are the main things I wanted to show you. And down at the bottom here is the amount of diesel exhaust fluid that is required to meet the Tier 2 bin 5 as a percent of the fuel over these operating ranges. You notice RCCI needs none, right, because it's going to meet the emissions without that. And the conventional diesel amount is shown down here. There's a lot of exhaust fluid needed, 5% of the fuel at high load. So how did we come to those conclusions? These plots here show the predicted NOx as a function of the main start of injection timing. The Euro 4 baseline had an injection timing, if you recall, near top dead center, and that's the point shown here. It had a gross indicated efficiency somewhere around 44%. So and a corresponding NOx value that was pretty high. This is for the mode 5 point. If we retired, or rather advanced the injection timing, so inject earlier than TDC, we see the NOx starts to increase, but so does the efficiency, right? So basically, by running at Euro 4, trying to meet this NOx target here, they've already sacrificed a huge amount of efficiency because the combustion is so late. All right, but we can operate at high NOx levels if we have SCR. So we can move up this line here. And by introducing this curve here says the amount of diesel fuel, diesel exhaust fluid, by having, say, 5% of exhaust fluid in our SCR system, we can knock this NOx value down to the Tier 2 bin 5 value. And in fact, then this is what we see for our efficiency curve when we take into account the fact that for every 1 gram per kilowatt hour of NOx reduction required, we're going to be using essentially that amount of diesel fuel, and we have to subtract that then from the overall efficiency of the engine. So basically, there is a trade-off here between fuel consumption and DEF consumption. Whereas with RCCI, as I mentioned, you don't need any of these after-treatment fluids. Okay, so then we can get to the comparison here. Let's focus first on the plot over here. This is NOx for the 5 different modes, mode 1 through 5. And the blue data that I want to show here is conventional diesel combustion equipped with SCR to meet the Tier 2 bin 5 targets. Okay, so that's this blue data. If we had not used SCR and had just operated as people used to do 20 years ago without worrying about NOx and just go for peak efficiency, we would get this black curve here from conventional diesel combustion. You notice this is a log plot, right? So we're talking about an order of magnitude increase in NOx. So remember that 10 grams, this is in gram per kilogram fuel here, but 10 grams of NOx for the same power output here corresponds to 10% of the fuel in the form of DEF. So you would need a lot of DEF. So what they've done instead is to change to compromise by changing the start of injection timing to reduce the amount of SCR that's needed. The red data you see here is the Euro 4 without SCR. That's where we started, if you like. And you can see that that's a significantly high NOx level, much higher than the Tier 2 bin 5 target. All right, so then, of course, the exciting thing is RCCI. Here, the RCCI and the diesel are very similar because basically we're running with just diesel fuel at light load. And then as we increase load, we add gasoline. You see our NOx levels are, again, an order of magnitude lower than those seen with SCR diesel. So that's exciting. But the more exciting thing is shown here. Here, corresponding to these low NOx values is the gross indicated efficiency. You can see RCCI has much higher efficiency than Euro 4, which is way down here. Euro 4 has those very late timings, so the combustion is really poorly phased to try to get these NOx levels, which are already much above the tier 2 bin 5. So this is very poor efficiency. If you go to tier 2 bin 5, which is the blue thing here with SCR, significant improvement in efficiency because of the after treatment being handled, which allows you to improve the combustion phasing. If you didn't worry about NOx, you would be able to do even better. But because of the fact that we have to worry about NOx and introduce SCR, we have this result. And then finally, the RCCI. Significant improvement over the baseline data, as you can see. So this is very exciting. Oh, and by the way, this plot here shows peak pressure rise rate. In other words, an indicator of the noise of the engine. And you can see that RCCI is really in the same range as all these other conventional diesel combustions. So if you take the cycle average over the entire 5 operating points, and I'm showing you here the cycle average NOx, the tier 2 bin 5 level is 0.4, which the CDC using SCR was designed to meet. We're even lower than that over the cycle. This shows the CDC baseline, much more NOx. And then here, if you didn't use exhaust fluid and just optimized the efficiency of the conventional diesel combustion, this would be the amount of NOx. But as I showed you, the efficiency there is still less than you have with RCCI when you average it over the cycle. The other thing that jumps out at you is we get no soot. Whereas if you look at the standard diesel combustion, even with SCR, there's a large amount of soot that has to be dealt with a particulate filter. So that's another issue with conventional diesel. So if you look at what these results show here is we meet the targets without after treatment. We have 8% improvement in fuel consumption over CDC SCR. Soot is an order of magnitude lower than with conventional diesel combustion. One of the issues, though, and I'm going to talk about this in a second, is that as with low temperature combustion, we have higher unburned hydrocarbon. And this is now basically where we're spending most of our time, is trying to reduce that unburned hydrocarbon. As I'll show you, most of it comes from the crevice regions, like in a gasoline engine. And that's because we have a pre-mixed mixture of gasoline in our engine. So we've been collaborating with the Oak Ridge National Labs. They have the same 1.9 liter diesel engine, except it's a multi-cylinder version of the engine. And they've operated it, this is actually pretty old data here. They've operated it by introducing port fuel injectors into the manifolds here for gasoline and then direct injector in the engine itself. They have the full engine layout. It's a Euro 4 engine. Basically, the first results they got, this is running at 2,300 RPM, 4.5 bar load condition, showed about a 5% improvement in fuel efficiency with RCCI on this multi-cylinder engine, while reducing NOx by an order of magnitude, reducing particulates or the filter smoke number by 2 orders of magnitude. But as I said, with an increase in CO and unburned hydrocarbon, and a reduction in exhaust temperature. That's basically what you're getting is you're converting some of that cylinder temperature into work in this combustion strategy. This shows the hydrocarbon emissions from conventional diesel, from early injection PCCI diesel, and from RCCI. This is the engine here with a diesel oxidation catalyst. hydrocarbons. So conventional diesel, because of those high temperatures in the combustion, has relatively low engine out hydrocarbon. PCCI also relatively low hydrocarbon. Essentially, you're using diesel fuel, which is quite reactive, so it's not a problem to burn the fuel, or less of a problem. RCCI, though, you see quite a lot of engine out hydrocarbon. Good news, though, is that if we pass it through a diesel oxidation catalyst, we can reduce that amount of hydrocarbon significantly, as shown here. So, and at the same time, of course, have very low NOx levels that don't require after treatment. So basically, diesel oxidation catalysts are like a three-way catalyst in your car, except they don't deal with nitric oxide. And so this doesn't seem like a big challenge, or at least it could be worse, let's put it that way. So RCCI is fuel efficient with emissions that can be controlled with a DOC, was their conclusion for that work. Since that time, they've also looked in more detail at the particulates. So here you're seeing particulate emissions. I showed you the slide before for conventional diesel, PCCI, and RCCI captured on a filter. You see quite a different looking particulate. As we saw before, these are experimental measurements, but our modeling predicted this. Very low particulate levels, similar to those that you'd have with PCCI, but quite a different type of particulate. In particular, you can see here that the diesel oxidation catalyst actually works on the particulates. So that is an indicator that the particulate actually consists of quite a high concentration of fuel, condensed fuel, that the DOC is able to oxidize, even with relatively low exhaust temperatures. So that's also good news. The other thing is, if you look at the size distribution of the particles, you had a question?
Was that the exhaust temperature after the DOC or before it?
This was engine out.
Okay.
Yeah. If you look at the size distribution of the particles, so this is the number density, if you like, number per cubic centimeter, versus the size of the particulate matter, you can see some significant differences between diesel combustion, particulate, and RCCI combustion. In particular, RCCI over here, over a wide range of particle sizes, is 2 orders of magnitude lower particle number than with conventional diesel. Conventional diesel is the red and the black here, before the engine out and after the DOC in the red. For PCCI, we see similar peak number densities, slightly different looking distribution of sizes. This plot on the right, this is a log plot, by the way. The plot on the right is a linear scale here, and it shows that the DOC really reduces the small particle count in its effect on the distribution. But I think the takeaway here is that essentially not only is the particulate completely different, but the number density is very low, which is also interesting because in Europe they have been talking about a number density standard for particulate. And so this plays into that as well. The other thing that I wanted to mention is that we have looked at RCCI in both light-duty and heavy-duty engines. And so this, just the last few slides here I wanted to show you on this topic, is where we compare the heavy-duty and the light-duty results. So, for example, in this case, we ran the engines at the same load. We tried to use some of our scaling, engine size scaling results to make sure that the engines were operating similarly. We picked this particular speed here because we were trying to attempt to scale heat transfer. Remember that in a small engine you have more surface area per volume than you do in a large engine. So we wanted to try to keep the piston speeds similar also. They ran at the same EGR rate with the same injection schedules, slightly different injection pressures, because in a large engine, in order to get the spray to penetrate a little bit further, we need a higher injection pressure. and everything else pretty much the same. So we want to compare the results from these two engines. And here are the results. Here we're showing nitric oxide, soot, gross indicated efficiency, and a measure of noise in the engine, pressure rise rate or ringing intensity, as a function of the CA50. That means the 50% burn crank angle. We can change this, remember, by changing the amount of gasoline versus the amount of diesel. So for example, for this red data here, for the heavy-duty engine, by changing the gasoline from 82% of the fuel to 89%, we can change the start of injection timing from the CA50 timing from 0 to about 4 degrees after top dead center. That's the advantage, one advantage of RCCI is controlling combustion phasing. The light-duty engine data shown here, where we've again swept the gasoline-diesel ratio to change combustion phasing. You'll notice that the engine efficiency curves here are pretty flat over this range of CA50. First thing that pops out at you here is that we're able to meet the 2010 emissions levels because we get very similar NOx and soot from the two engines for these different combustion scenarios. But here you notice a significant difference in the efficiency. The heavy-duty engine has efficiencies in the 55–56% range, whereas the light-duty engine is around 50%. So it's a significant difference, 5 to 7% difference in efficiency between the light-duty engine and the heavy-duty engine, everything else being the same. Also important to look at these numbers. For a typical heavy-duty diesel engine, the gross indicated efficiencies are around 48%. You can see we're getting significant improvement over that. And for light-duty engines, about 45%. So again, significant improvement. Yeah.
Why are you now choosing to run these with EGR, even though you showed before?
So again, it depends on the fuel that you use, because the EGR is helpful to keep the temperatures low. And so you're basically playing a game between compression ratio, EGR amount, and fuel. It just so happens that for higher loads, having EGR is advantageous when you have gasoline. But if you use ethanol, it turns out you don't need EGR until you get to really high loads. So it's all a question of optimizing the temperatures. So if you look at where the energy goes, this plot here basically divides the fuel energy expressed in terms of, say, a fuel energy or a mean effective pressure into combustion losses, which are these guys over here. You can see that the small engine, the blue one, has about a 2.3% difference in fuel energy than the large engine. So that's where some of the inefficiency comes about. In other words, higher unburned hydrocarbon and CO. If you look at the next here, this is the heat transfer contribution. Again, quite a difference in the small engine, about 3.4% of the fuel energy, more of the fuel energy is lost to heat transfer. And we'll see some reasons for that in a second. Exhaust energies are similar, but a little bit more is lost in the small engine. And this is what explains the difference then in the gross indicated efficiency that is seen between the small and the large engine. Okay, so to understand this a little bit more, we've done some simulations. And one of the things that comes out of the simulations is that tracking the unburned hydrocarbons and the CO shows you that it's all coming from the crevice region near the cool liner here. And that's pretty much true for gasoline spark ignition engines as well. So that's essentially one problem that we have to deal with. We've spent a fair amount of time and continuing to spend time looking at the design of the ring pack here and concluding that we really want a ring pack that looks more like a gasoline engine's ring pack than a diesel engine's ring pack. Diesels don't worry about fuel being pushed down into the crevice here, whereas gasoline engines do. So that's one aspect here. The other thing that I mentioned was the heat transfers. So that was another contributor. The small engine operates with a high swirl ratio, the large engine with a low swirl ratio. And what we found is that the swirl ratio is actually a negative because high swirl means high convective velocities, which means high heat loss. So operating with a low swirl is advantageous. Similarly, the engines have a different surface to volume ratio. So we've spent quite a bit of time redesigning the piston of the light-duty engine to try to reduce the amount of surface area. Obviously, a flat piston is the best scenario in that case. There's the lowest surface area to volume. But it has some other problems. And then, of course, the fact that this is just generally that even though the light-duty engine runs at a higher speed than the heavy-duty engine, there's still a difference, and that contributes some to the heat transfer. So basically, if we look at where this work is going, yeah?
On that swirl question, earlier you showed that in your initial simulations that the best case was a swirl of like 3. Does that have to do with the spray angle that you
So there was conventional diesel combustion, okay, where basically you spray the fuel and now you want the swirl to spread it out, spread the fuel out and mix it appropriately to get low soot. And that's what was great. Here, the injection is finished by 30 degrees before top dead center. And all that you're now waiting for is for the fuel to cook and ignite. So swirl really doesn't do you any good here. Maybe a little swirl is helpful, but you don't need the same high levels of swirl that you do in conventional diesel. And so basically, that's one of the things that we're looking at is trying to reduce the swirl in the light-duty engine by redesigning or looking at the configuration of the intake ports. Thanks. Okay, so this sort of summarizes where we're going. This is the Euro 4 operating point. In other words, when we run RCCI using the Euro 4 boost intake manifold temperature and swirl ratio, this is the operating point. This is, again, CA50 versus gross indicated efficiency. If we make some changes to the engine that include dealing with heat transfer losses, we think we can increase the efficiency at this particular operating point. This is the high load point, from about 48% to 53%. So that's even better than any of the results I've shown you, which were already better than we had before. In fact, we showed before 8% improvement in fuel efficiency. We think we can get another 10%. So how do you get this 10%? So if we look at, for example, reducing the swirl to 0.7, we can see we can get significant improvement here. The other thing is to get that unburned hydrocarbon question dealt with. Aside from redesigning the piston, if we can make the piston and cylinder walls at a higher temperature by going from aluminum to steel piston, we think we can, again, improve the efficiency. And that's, I guess, going one of these curves here. Yeah, this is the green curve. And then if we apply all of these things together, namely low swirl ratio, high wall temperature piston, a steel piston, we can get up to this type of efficiency, which is 53%. So that's where we're currently spending our time. Remember that the Department of Energy has certain goals that it has set for both heavy-duty and light-duty engines. We think we can get as much as 18% improvement in fuel efficiency, which is consistent with their goals. Yeah?
Regarding the walls of the piston temperatures, so are you having to go back and redo your estimations for what the walls and the piston heads
Absolutely.
are for each of these cases?
Yeah, so in fact, one of Professor Gandhi in our group has, and his students have instrumented pistons in these engines with heat flux probes and made measurements of piston temperatures. And they've seen basically very low piston temperatures in RCCI. We want to increase those temperatures. So one way to do that is, remember I showed you when we were calculating piston temperature, there's an oil jet that comes up under the piston that keeps it cool. You can turn off that oil jet or reduce it somehow. That raises piston temperature. So the things you can do to try to get rid of that last few percent.
But for each one of your simulations, are you, every time you do a simulation, are you going and adjusting that based on the simulation?
We've just assumed values that are representative. from those conjugate heat transfer simulations and measurements. But yeah, we would like to do that.
So all these studies show you start with basically a diesel engine you already have and then modify it. Have you thought about going the other way, using a high compression gasoline engine and then modifying it?
Yeah, I'd love to do that, but you know, I only have 2 hands. But that's a great idea. Yeah. So to summarize this part of the presentation, I've spoken a lot about RCCI. I've shown you that it came from using CFD model optimization and then validation in the lab. It provides clean, quiet, efficient combustion over wide speed and load ranges. We've tested it over very wide load ranges, also with our collaborators. We can meet the heavy-duty EPA emissions regulations without the need for NOx and particulate after treatment, and still have gross indicated efficiencies that are significantly higher than for conventional diesel, even with SCR. For the the light-duty engine, we have low NOx and PM emissions with less EGR needed. In fact, as I showed you over the FTP cycle, we only used EGR at idle and at the higher load points. Other nice thing about this is that outside the FTP, the engines are unregulated, so you can revert back to a diesel engine if you like, and still maintain the high performance of a diesel engine. Obviously, that's not, in the long term, going to be a solution. So I mentioned then that at idle we use some EGR and at higher loads. RCCI, the modeling has shown that we can see about an 8% improvement of fuel consumption over CDC conventional diesel with SCR. We can meet Tier 2 bin 5 without NOx after treatment or a DPF, but diesel oxidation catalyst will probably be required for unburnt fuel reduction. We've also seen that there's room for further optimization using higher boost pressures. This lowers heat transfer losses, higher piston temperatures, again, to help reduce the unburnt fuel, and also the delta T for heat transfer. Reduce swirl to reduce convective velocities, again, reduces heat transfer, reduce surface area, steel piston, optimized crevice design. So we will continue to work on this, and we're actually right now installing an RCCI engine in a vehicle, a student vehicle on campus. This is the Eco Car, and one of my grad students is excited. He's going to be doing this job, and we'll see how it works. Should be able to drive. This is a series hybrid, so basically we'll run the engine at one speed and one load, charge the battery with the engine. It'll run on ethanol and biodiesel, so basically very little fossil fuel, and it's we'll see how it performs. So to finish this, I have a bit of time. I want to just summarize the future of this modeling that we've been discussing. We can maybe take some questions. And then I wanted to talk about the very long-term future, just for fun. So let me just talk about the future of CFD modeling. I spoke largely about RANS models, Reynolds average, Navier-Stokes turbulence model. We're doing some work at the Engine Research Center, Professor Rutland and his students, on implementing higher fidelity turbulence models, large eddy simulation. And if you compare results with those seen in the experiments, these large eddy simulation models seem to be doing a very good job. In fact, almost 20 years ago, Professor Rutland made this plot here where he plotted computer speed versus time. He started in 1980 out of grad school, so this is a projection. And he used Moore's law to draw this red line here. And then he didn't believe that Moore's law would necessarily continue, so he put this dotted line in there just in case. And his predictions were that, by the 2000s or late 1990s, K epsilon would be superseded by large eddy simulation, and then finally direct numerical simulation in the 2020 and beyond time frame. So if you just look at that here in terms of the history of CFD, in the 60s, basically, we had zero-dimensional models. In the 70s and 80s, we had those 1D and possibly 2D models. In the 90s, three-dimensional models started to appear with 1 millimeter type of grid resolution. And I've been talking a lot about those kind of models in my presentations here. In the 2000s, we basically improved those models incrementally and essentially improved the turbulence models. In the 2010s, 2020s, we'll see even more resolution, for example, looking at the nozzle flow processes, cavitation, and so on, improving our description of the chemical kinetics. So basically, this has been a long road here, but I think the models are at the point now where they can be used in industry for design, and they can be used to look at things that you may not have thought of without the help of the computer. So that was what I wanted to talk about in terms of modeling. And maybe we should take just a few minutes for questions here. And then I want to just go into the really far future and talk about a paper that I think we should all take a look at sometime. Yeah.
How did the cycle-to-cycle variation for combustion phase?
So it's really,
RCCI?
for RCCI at light to medium loads, it's very stable. It's when you get to high load that small changes in, for example, intake temperature or the amount of fuel in your injections vary slightly. Then you start to see some increasing in, say, COV, the coefficient of variation of, say, your IMEP. But they're generally fairly low, less than 5%, even at pretty high loads. So it's all an issue of how tightly you can control the intake pressure, intake temperature, and the quantity of fuel injected, and the timings and so on. I think that one thing that's going to be clear with these advanced combustion engines is you're going to need some kind of feedback control. People are talking about in-cylinder pressure measurement. Already you can buy cars on the road that have in-cylinder pressure measurement feedback control. So it'll be pretty much something there for the future. Yeah.
Can you comment a little bit about low exhaust temperatures and hence the low exhaust enthalpies on the effect of less extractable boost or effectiveness of the oxidation catalyst?
Yeah, so that's a big concern. So you have to look at the whole engine system. What we're focused on is the combustion process, obviously. But in order to drive a turbocharger, you need a certain amount of exhaust enthalpy. And you're essentially trading off between work and the piston and work to drive the compressor. So multi-stage and maybe even supercharging is the type of thing that people are looking at to try to extend the air preparation. We're also looking at low temperature EGR. So basically you take all the exhaust through the turbine and then feed back the EGR downstream of the turbine. That turns out to be really effective because you get more of the exhaust work that way. You don't bypass the turbine. So there are, what you're asking is a complicated question, and people are starting to look at that. The Oak Ridge people have system simulation models that they are already looking at, and even vehicle simulation models. And we ourselves are starting to look at GT power models of the whole system and trying to optimize it. But you have to remember that if you don't need SCR, remember I told you yesterday, half of the cost of the engine now is the after treatment. If you don't need that, you have room to do other things and still maintain low cost. Also, we use low injection pressure, so you don't have to go to 3,000 bar injection pressure, which was another solution that people are looking at. So essentially, it allows you to rethink engine design. Yep.
I think criticism you hear a lot about is having multiple fuels.
Yep.
And people just don't like the two ways to do it, I guess. Well, do they ever have questions on the initial cost? Seems like having several injection systems would
Sure, right. So it turns out
expensive.
that a port fuel injection system is pretty much free. I mean, it's very cheap. You don't need a high quality injection system. So that's all we're really adding. And we're subtracting from the high pressure diesel injector that is required for conventional diesel combustion. So it's a trade-off.
So these fuel delivery systems aren't as complicated as
No.
Okay.
No. Yep.
If you look at
Absolutely. So we haven't done experiments yet, but they're planned. We're building a couple of labs to look at that. But we've done a lot of modeling work. Published a paper at the SAE this year that indicates that with natural gas, you can run with pretty much no EGR up to very high loads. And again, with optimized injections, which we did with our CFD, you can get very good performance. Slightly worse than with gasoline diesel because it turns out natural gas flame temperature is higher than with gasoline, so your heat losses are a little bit higher. You suffer a couple of % in efficiency.
Secondary fuel is diesel?
Diesel, yeah. Yeah, I haven't thought of doing cetane improver with natural gas.
Have you looked at that method for season?
I don't know. No, we have not. I don't know if you'd see advantages there. We'd have to look into that. One more? Yeah.
Have you looked at the PM size distribution as far as if you're getting smaller or larger, if there's any difference?
Right. I think I showed you a plot on that. You know, basically the size range. I hope I don't have to go back too far. Yeah. Size range of the particles is, you know, pretty similar. I mean, the measurement device cuts off at a certain point. And here are the larger particles, but the range is similar for all of these combustion modes. It's just the number density is very different with RCCI. Okay, yeah?
Talking about the needs of industry combustion research, do you see that easier for the companies to define what they want, or is it easier for you to market a new idea to the company? How much in their share?
I need to know the answer to that question if I want to be rich. Huh? I don't know the answer to it. Basically, you know, I don't mean to be disparaging here, but certain companies have resisted change because basically it's a lot easier for status quo than it is to do something different. And that includes seat belts. You know, I mean, any change is a disruption. So there have to be strong incentives. And fortunately, the EPA is a very strong incentive. So, yeah.
Sort of feeding off of that is how much retooling would be necessary to move to something like the concept you're talking about?
Like I said, you'd have to have port fuel injection, depending on what you want to do. The people at Oak Ridge basically drilled 4 holes in the intake manifolds and put in port fuel injectors. They had a engine control system that allowed them to essentially extend it to 4 more injectors, and they were done. Now, they didn't necessarily get the most optimum performance, but that was relatively simple.
Can you elaborate what exactly a port fuel injection system is?
So in the intake manifold, you'll inject the fuel directly into the intake flow.
Oh, so this isn't through the valve that you can normally see in the head of a gas cylinder?
Yeah, so it's not an in-cylinder injection. It's in the intake manifold.
So that helps
it's really cheap. Yeah.
So since you're running such high gasoline numbers, you having to install like a traditional like throttle body then to regulate?
Well, no, because you'll be using your port fuel injector to determine the amount of fuel injected.
It's just you control all that just that way.
Just with that injector, like in your car. I mean, if you have a PFI injection system, which most cars have now, that's what you use. All right, let me finish with this last part here because I think you might find this interesting. This paper by Professor Abbott made me rethink a lot of things. And since you guys are going to be the people designing engines 20, 30 years from now, maybe you need something to stimulate your thinking about what's going to go on in the longer term. Okay, so he looked at it this way. How much energy do we use on this planet? And it works out that for the 6 billion people here, we are each running 25 100-watt bulbs. So that's how much energy we use. And if you compare that energy with, the total energy used by New York City and total energy due to photosynthesis, we're in between those two there. So that's a lot of energy. But the important thing is this one. The amount of sunlight that's coming down to the Earth is orders of magnitude more than this. So basically, if you take a look at what we have here on our planet, and he goes into a lot of detail in this paper, we have enough uranium to supply that 15 terawatts for basically 5 years. That's not a long time. Right? We have enough fossil, using known reserves and so on, for 42 years. Natural gas, 60 years, and coal, 130 years. Okay, so 130 years from now, maybe you don't worry, but your kids and their kids and their kids are going to worry. So what are we going to do? The other thing is that all these fossil fuels are really precious. We need them to make fertilizers, plastics, to lubricate, and so on. And then the other point he makes is we probably want to keep this uranium because one day we're going to want to escape this planet, billions of years from now. So how are we going to do that with today's energy sources? Well, nuclear is certainly something to consider. Okay, so if you look at the consumption of energy, if you just assume that it was all transportation, you can see that 5 billion people driving a car for 1 hour a day basically would be using 2/3 of the current consumption in the world. And so we're pretty lucky right now that the whole world isn't driving cars. If the whole world starts driving cars, we're going to be in real trouble, right? So anyway, if you look at it from that point of view and you say, well, how are we going to deal with energy on this planet when we run out of fuel? His argument is there's only one source of energy that we can count on, and that's the sun. So here it is. It's a big reactor. And basically everything else, all these other things that people talk about, hydroelectric, waves, solar, everything, it all comes from the sun in one form or another because the weather is created by the sun. That gives you the wind and so on. So the sun is really our source of energy. So we better think about it and include it in our thinking of energy. And this is what led him to consider the solar hydrogen economy, which is what he's advocating. So basically, if you look at the amount of solar radiation, it says here, solar energy incident on the Earth in 1 month is more than all of the energy in the world's fuel resources combined. Huge amount of energy. So the usable solar power that's incident on the Earth is 5,000 times our global energy consumption. Deserts make up about 9% of the world's surface area. And his argument is if we tap sunlight on 1% of the Earth's surface, so we don't use all the desert area, and we convert the energy incident on that part of the Earth at an efficiency of 1%, we'll be able to meet the 15 terawatts. Yeah.
You know what he means? Land surface or total surface?
This is up here, it's total surface, but here he's just speaking on the desert. And he's saying you only need 1% of the Earth's surface to get this type of the energy that we need at a very low conversion efficiency. And people are already doing that. Here are these solar collectors. His idea is that you take the solar radiation, focus it here, and basically boil water, make steam. And you use that steam to drive the economy, the hydrogen economy. So you've got the sun, focus the sunlight, you make steam, generate electricity. You've got a grid here to distribute the electricity. You need water, because you're going to need that for the hydrogen. So you've got desalination here. Produce hydrogen. It can be either liquefied or it can be stored as compressed gas. But ultimately, this is a completely renewable, reversible cycle because you've got just a permanent supply of energy from the sun. You've got all this water. If you capture the water after you burn it in your vehicle, you can actually even close the cycle. So, everybody said, oh, hydrogen. In fact, there was a big push on hydrogen a few years ago. But because fossil fuel is so cheap, nobody really takes these options seriously. And, if you think about it, what are the other options? Batteries, right? We only have enough lithium on the planet for 23 years. That's if all cars ran on batteries. Fuel cells, they require exotic rare materials. We're going to run out of those. The internal combustion engine can be made out of iron ore. We don't need exotic materials for it. So basically, it's sustainable using available materials. Okay, so internal combustion engine actually has a lot of advantages over some of the alternatives. And in fact, it's not an impossible task to make an engine run on it. BMW has this engine here operating on, in this case, liquefied hydrogen, Ford, and so on. So basically, internal combustion engines, if you think about it, are simple. They've been around 100 years. They don't require these advanced materials, especially if after-treatment is not required. So it definitely makes sense to be thinking about this. It's also, as I said, we can rely on the sun for at least 1 billion years. In fact, in his paper, he makes one point which I never thought of, and that is if you make hydrogen out of water, hydrogen being light can actually escape the Earth's atmosphere. And eventually the oceans are going to go dry in like several billion years. But by then, I don't think we have to worry. The fact is that we have just this huge time span for energy. So anyway, this is definitely a paper that I recommend that you look at. His point, and I totally agree, is that we have cheap energy, and it's really distorted the world's economies and priorities. This cheap energy has allowed us to reach 6 billion people, and people estimate we might be up to 10 or more billion. And that's just because we had cheap energy available. In the next 30 to 40 years, when you guys are retiring, you're going to have to see major innovations in internal combustion engines because there will be dwindling resources. There will be very noticeable environmental impact. And we just can't go on using energy at the rate that we are currently. A lot of this solutions here, battery, fuel cell, nuclear, are really only short term. And in many cases, we want to keep those precious resources for future generations. And really, the only sustainable long-term energy source is the sun. There's no other that we can think of. And obviously, we're going to have to do a lot of research on improving the efficiency of electricity generation, hydrogen production, storage, and using hydrogen in an engine. It's going to take a lot of time, but this is an important conversation that took place in 1931 here between Edison, Ford, and Firestone, where Edison said, I would put my money on the sun and solar energy. What a source of power. I hope we don't have to wait until oil and coal run out before we tackle that problem. Anyway, that's, I thought, a really interesting paper, and I recommend that you take a look at it. So we have a couple of minutes left. I was told to keep you guys here a little longer so we don't have a collision in the lunchroom. Any more questions? Yes?
It's interesting that you had a lecture on hydrogen idea, but it seems to be going back in the discussion about whether you get more excited about the hydrogen energy.
Right. Well, it's an issue of cost, right, and also motivation. If you had no other fuel, what choice do you have? So that's something that he points out in this paper. 30, 40, 50, 100 years from now, you're going to have to think of something different. And maybe it won't be your problem, but it'll be your kids' problem and their kids. And we better start thinking about that.
Have you also come across been involved in discussion about using coal dust in internal combustion engines?
You saw there's enough coal for 132 years. Right? So yeah, we can use that for a while.
So what about using that in an internal combustion engine?
Yeah. Well, that's what Rudolf Diesel did, right? He ran on coal dust. And I think, who was it? Bill Green pointed out that using solid fuel is just not a good idea. It's very hard to transport, hard to deal with. So liquid fuels have many advantages.
In this paper you mentioned, did he specifically advocate using hydrogen versus some other commodity chemical? I mean, it seems like hydrogen has so many issues. A lot of other people are proponents of in this long term using sunlight to drive,
biofuel,
liquefaction and gasification. But just when you have carbon there, it's nice because, well, then you get liquid.
Yeah, so that is definitely an issue. You know, compressed hydrogen is hard to handle. Liquid hydrogen even worse. But the good thing about hydrogen is, you know, it comes from water, and we have oceans full of this stuff if we can desalinate, and if you have the electricity to do that, which you get from the sun, water makes sense.
But did the address, you know, you just want to, like, you know, add biomass, and the great thing if you do partial electrolysis on water, you get the hydrogen, then you just hydro-treat any organic material you want. And then you end up with the same liquid hydrocarbons doing it now.
Sure.
It takes more work, but I mean, if we're talking long term, what are your other options?
Right, so we have the same liquid hydrocarbons that we have now, but we have to use precious metals in our DOCs or our catalysts. And how long are we going to have those precious metals? You know, 100 years maybe, but you know, this paper wants you to think 1,000 years.
I mean, some of those metals are just iron.
Yeah,
That's true.
So this isn't going to happen overnight, you know. But I think his point was that, you know, if you don't think about this as the end state, then how are you going to get there? You know, you have to kind of blend into it basically over time, and that's basically what Thomas Edison was saying in 1930. But you've got very good points.
It's just curious because I've heard other people recommend other economies like, oh, hydrogen's got so many difficulties. You know, we could just as easily make this, you know, say methanol.
Sure.
That's how we get hydrogen in the first place nowadays.
It's a very good point. Okay, I think Ed is here to tell us we have to go to lunch.
Yeah, but first of all, we should thank our lecturer. Reitz and other lecturers are really good. And especially come here, they're busy people. So, really.
Well, thanks for inviting me. I enjoyed the questions. It makes me think.
I'm sure the lectures
Thanks.
Okay, you're the second group for lunch.